Hey guys, so yeah, you would have, through your watching of the Edpuzzle, hopefully understood how to calculate the molecular formula and the empirical formula, or at least have an understanding of them. Now I'm going to kind of go more in depth with some of the math, because the math is complicated and challenging. But the initial empirical and molecular formula, just knowing the difference, isn't too challenging, so I thought that intro video would have been helpful. So let's talk about what are some of the objectives and look at how we can cover all of those, right? So know the difference between molecular and empirical formula. I was hoping that video, like I said, would get you there. Know how to calculate empirical formula from molecular formula. Again, that's fairly easy math, so I gave you those two first, and then from there I thought we could go into going into the percent composition, which the way the book presents it actually presents percent composition first, but I think it's better to do it the other way around. Understand that molecular formulas may have the same empirical formula, so several different compounds may all have the exact same empirical formula. And then know how to calculate the percent composition of each element within a compound, and how to calculate the percent by mass of each element within a compound. So real quickly, I'm just going to do an overview of molecular formula versus empirical. You watched the Edpuzzle, hopefully, and completed that. But molecular formula is the actual chemical makeup. Okay, so whenever you are told this is the molecular formula, that's what that element's molecular formula is. So sodium chlorides is NaCO. Waters is H2O. Methane gas is C3H8. So there's certain things that's the molecular formula. It's never going to change. The empirical formula is just the ratio of the elements within that compound, the lowest possible whole numbers. So surprisingly, all those ones I mentioned all have the same empirical as molecular formula, because you cannot simplify the ratio of atoms of the different elements that are in it. Okay, but if you can, then that would be the empirical formula. So if C2H4 is the molecular formula, its empirical formula is then CH2, because you can simplify both of those numbers if you divide them by 2. So let's look at percent composition. So percent composition is going to be the percentage of the whole, okay? And so remember, the percentage of anything is the part over the whole times 100, okay? That gives you a percentage. When we're looking at elements in a compound, we're looking at the mass of the element divided by the molar mass of the entire compound multiplied by 100. That'll give you the percentage of the element that is that element, okay? So let's look at the percent composition of sodium chloride. So what is it? So start with the mass of each of your individual elements. So take the mass of sodium. If you look on the periodic table, it's 23.0. There's some dots there, or some numbers after that, but if we look at sodium's 23.0, and since there's only 1 in this compound, we multiply it by 1, we get 23.0, and we're looking at molar mass, so it's in grams. Now we do the same with chlorine. The mass of chlorine is 35.5. When we look on the periodic table, multiply that by 1, and you get 35.5 grams. So now we can figure out what's the total mass of sodium chloride as a compound. Add them together, we get 58.5 grams, okay? Now, to figure out how much of sodium chloride is sodium, we put 23.0 grams over 58.5 grams. Multiply that by 100, that will give us now the percent mass of sodium that is, the percent mass of sodium chloride that is sodium, okay? And we can do the same thing with chlorine, and we get 35.5 grams over 58.5 grams. And those, if you do the math, you get 39.3% of sodium chloride that is sodium, and you get 60.7% that is chlorine. So this is the percent composition. I'm asking for the composition of all of sodium chloride. So I got to do each element in it, okay? Let's look at another problem. Let's look at the percentage of ammonium gas that is nitrogen. Okay, so here the question's asked differently, right? In this last one, percent composition of sodium chloride, so I want all elements. In this one, I just want nitrogen. So ammonium is NH3, okay? And so we start by figuring out what's the molar mass of NH3. So if I look up nitrogen, it's about 14, and then each of the hydrogens is 1.01, so 1.01 times 3 gives me 3.03 plus 14. I get 17.03 grams per mole. Okay. Then I'm going to say that 1 mole of this, right, contains 14.01 grams of nitrogen, and so I know that that's nitrogen's molar mass. So I put one over the other, multiply it by 100, and I get 82.27% of ammonium is nitrogen. Okay. So I'm going to give you now a problem to try. So what is the percent composition of H3PO4? H is 3.08%, P is 31.61%, and O is 65.31%. And of course, I'm not showing you the math, but you could have done that math by taking the total mass of the whole compound, right? Figuring out what that molar mass is, and then taking each individual element's mass out of the whole, multiplying it by 100, right? So since there's 3 H's, I got to multiply 1.01 times 3. There's only one P, so I just multiply it by 1. There's 4 O's, so I multiply that by 4. Each of those values, then, I'm dividing by the whole and getting my percent composition. Okay, now what about empirical formula from the percent composition? So because percentage means out of 100, I can, if I'm given a percentage, but not masses, right? So I've given you how to calculate from the percent mass. But if I don't have the mass, we can still figure out the empirical formula, right? So let's look at an example. I have 100 grams of a sample that is made up of 40.05% sulfur and 59.95% oxygen. What is the empirical formula for this compound? So let me do the math for you here. Okay, so let's start by doing this step by step. Step 1 would be to change those percentages that you're given, the 40.05 and the 59.95, from percent to grams. Because remember, this is out of a 100-gram sample. Even if it wasn't telling you it was a 100-gram sample, but they give you these percentages, because they're a percentage out of 100, you can convert them into grams, and then that way the total compound, you're looking at 100 grams of the sample of that compound. Okay. So step 1, change percent to grams. Step 2, so let's do that for both sulfur and oxygen. Okay, there you go. And then step 2 is going to be to take the amount in grams of each element and multiply it by the molar mass of the element to get the number of moles. So I'm going to take 40.05 grams of sulfur times the molar mass, right? Now, I could do that one of two ways. I could either do 1 mole over the mass that I get from the periodic table for sulfur, or I could do the amount of grams over 1 mole. Which do you think it would be? If you put moles over grams, that would be correct. So let's look at this first problem and the second one. So right here's this first setup, and then when I do the second bit, right, I put 1 mole of sulfur over 32.07 grams of sulfur. I figured 32.07 from the periodic table and also the 16 from the periodic table. I do my math, I get 1.249 moles of sulfur to 3.747 moles of oxygen. Those numbers aren't whole numbers. I can't make a chemical formula out of that, can I? What do? Here's where step 3 comes into play. Move this screen up here. Okay, so at this point you need to take the lower of the two numbers and divide both of them by that number. Remember, anything divided by a number, if you're dividing everything in that by the same number, it's going to be okay. It's not gonna change anything. So if I divide both of these by 1.249, since it's the lower of the two, I'll get 1 for sulfur, right? And I'll get 3, if I do this math, for oxygen, okay? And because I have essentially 1 mole of sulfur to 3 moles of oxygen, that's equivalent to saying that this compound would be SO3, right? 1 sulfur to 3 oxygens. Okay, so let's move on to the next one. So now I'm going to give you an example to try. So what's the empirical formula for a compound that is 32.37% sodium, 22.58% sulfur, and 45.05% oxygen. So work yourself through this problem and submit your answers. So the formula that you should have gotten would be Na2SO4. Alright, now what happens if I do the last step and do not get whole numbers? So if we go back to that one where I ended up with numbers that were pretty simple and I divided and I got 1 and I got whole numbers. What happens when I don't? So let's try another problem. Let's look at the empirical formula for a compound that's 48.64% carbon, 8.16% hydrogen, and 43.20% oxygen. This must all equal 100% in total, so just kind of keep that in mind. If your numbers don't add up, something's wrong, something's missing, okay? So let's do the same steps we did before, right? Convert to grams, so take all those percentages and make them grams. 48.64 grams of carbon, 8.16 grams of hydrogen, 43.20 grams of oxygen, okay? Multiply them by the molar mass of each, so, go back, do the molar mass of carbon, molar mass of hydrogen, molar mass of oxygen. Again, mole on top, grams on bottom. You should do that math and you should get 4.050 moles of carbon, 8.10 moles of hydrogen, and 2.700 moles of oxygen. Okay, next step, if you remember, is to divide each by the lowest of those, the smallest of those numbers, which is the 2.700 moles. Okay, when I do that, what I get is 1.5 moles of carbon, 3 moles of hydrogen, and 1 mole of oxygen. Then I'm going to multiply all those by the lowest number. That will give me whole numbers for each. Okay, because you see 1.5 moles is not a number I can put next to a carbon, right? I can't put C 1.5 as a subscript, right? The other two are whole numbers, 1.5 is not, so I need to get it to the lowest number. So if I multiply these by 2, then I will get each of them to be the lowest number they can be, okay, and get the lowest ratio of whole numbers for this compound. So C3H6O2. Great, okay. So now I'm going to give you some practice problems to try on your own, and you can tell me what your answers would be for these. So propane is composed of 81.82% carbon, 18.18% hydrogen. What's its empirical formula? Okay, so in that problem you got to convert those into grams, and then you're going to have to multiply it by their molar masses. Number 2, CaCl2 has what percent composition? Okay, so there we're asking not just for just calcium or just chlorine, but the entire composition. So you got to do both calcium and chlorine. And then number 3, determine the empirical formula for ilmenite if a sample of ilmenite is found to contain 5.41 grams of iron, 4.64 grams of titanium, and 4.65 grams of oxygen. In this example, since you're already given a certain mass, just multiply those masses by the molar mass for each iron, titanium, and oxygen. Okay, you don't need to convert them into anything. Just take those values they're giving you, they're already in grams, and multiply them by the molar masses. Okay, then from there, continue to follow the steps to calculate for the empirical formula. Okay, including, if you need to, multiplying the numbers at the end to get them to whole numbers, to the lowest whole number ratio. Okay, so why don't you try all 3 of those, and then I will share with you the answers. So the answer to number 1, CH3. The answer to number 2, 36.11% calcium, 63.89% chlorine. The answer to number 3, FeTiO3. And that is where we're going to stop here, but that kind of covers the ending of chapter 10, and so the next thing I'll be doing is a presentation on a review of the chapter and the topics that are in it, so that we can take an assessment on it.